Hey students, Friday here. The goal of this video is to help you have a great breakfast experience understanding the nature of Earth's insides. In this video, we'll discuss the inside of the Earth and how the Earth is layered. And this starts by you imagining a hard-boiled egg. So there we go, an egg on the screen. And when you imagine a hard-boiled egg and eating it, what do you have to do with that egg before you eat it? Yeah, you have to crack the shell and peel it off. Imagine the Earth is like a cracked hard-boiled egg before it has been peeled. In our first large group, we learned that Alfred Wegener knew that the crust of the Earth was broken into pieces. But he didn't have any idea what was down below. Many students ask the question, how do we know what's down below the surface of the Earth if we have not drilled very deep? We haven't drilled any farther than a few miles down into the crust of the Earth. Over the course of the unit, we're going to understand how scientists have gotten creative with measurements to help them to understand what is inside the Earth without being able to actually go down there. And in this video, we're going to have an overview of the different layers of the Earth so you can understand what's down there, and as we put the pieces of the puzzle together, we're going to see how scientists have used data to understand what is underneath the surface of the Earth. So this image shows the Earth split up into different layers. If we imagine that we had cut the Earth in half and then we're able to pull the different layers of the Earth apart from each other, this is what we see. On the left is the crust. It's what we're most familiar with when we look at the pictures of the Earth from space. The crust contains the continents and the oceans, and I'll break apart what the crust is made out of here in a moment. The next layer to the right, that red layer, is the mantle. And the mantle is where a lot of the action is going to be happening that we're going to focus on for how the surface of the Earth changes. The next layer to the right is the outer core. The outer core is very important to us because without the action of the outer core, we would not be able to survive the solar wind. The action of the outer core is also what produces the aurora borealis and the aurora australis. So if you remember the beginning of the year when we learned a little bit about movements from the sun potentially impacting Earth, the right of that is the inner core. The inner core is the solid iron portion of the core of the Earth where the heat from the Earth originates from. And in a moment, I'll tell you a little bit about why there's heat coming from that direction. So this cutaway shows us once again as if the Earth were cut in half, but now we are looking at it from the side, and each of those different colored layers shows a different portion of the layers of the Earth. We're going to start with the very top layer, which is the layer that we interact with and live with. Notice that the very top portion of the diagram says atmosphere. We spent some time earlier in the class talking about how Earth's atmosphere developed, how the gases changed over time, and the atmosphere contains the air that you and I breathe. Now, below that, we have the outer surface of the Earth. You can think of this as like the shell of the cracked hard-boiled egg. We call this the crust, and the crust is also scientifically known as the lithosphere. Litho means outside, sphere means layers, so lithosphere is the outer layer. The crust is solid, but not all parts of the crust are the same. The crust underneath the oceans is frequently very different from the crust that makes up the continents. Let's break out the crust into two different sections. You can divide the crust of the Earth into two types of plates. You can sort of imagine the pieces of the broken crust as like dinner plates that are floating around on the surface of what's underneath. We'll talk about how that floating happens in another video. Continental plates are the thickest plates on the surface of the Earth. They're made out of a rock called granite. Granite is a rock that is very hard. People like to make countertops out of it because it looks very, very nice when polished. But granite is actually a less dense rock than other rocks. In this case, density, if you remember back to middle school, means the amount of stuff you have in a certain space. So continental plates, since they are made out of granite, actually float higher on the liquid hot magma, Mr. Powers, that is underneath that. Continental plates are 20 to 25 miles thick, and it is very difficult to dig any distance beyond a couple of miles into continental plates. You can think of continental plates as, since they float higher, the waters of the ocean do not affect what is in the land that is floating higher on the rock underneath it. Oceanic plates are thinner. They're 7 to 10 miles thick, and they are more dense than continental plates. That's going to be important when we think about how the Earth's crust changes as things underneath it move. The rock that oceanic plates are made out of is called basalt. It is a black volcanic rock that is more dense than granite, so oceanic plates sink more into the liquid rock than continental plates do, and that produces these giant valleys that water on the surface of the Earth collects into that we call oceans. Back to our diagram. So that's the basics of the crust. Now let's go into the mantle. The mantle is divided into two layers, the upper mantle and the lower mantle. The upper mantle actually has another name for it, and that is the asthenosphere. Astheno refers to movement, and so asthenosphere is moving sphere or moving layer. The asthenosphere is a layer of rock that is hot enough and under enough pressure that it can actually move as that heat cycles through that layer. And we'll spend a whole other video talking about how that cycling happens. The lower mantle is more rigid than the upper mantle, but it is still in a plasticky liquid-like state. And so I think what surprises students in this section when we're learning about the layers of the Earth is that depending upon the combination of temperature and pressure that happens inside the Earth, that influences what state of matter these rocks can exist in. As you get closer to the inner core of the Earth, the temperature increases and the pressure increases. Gravity is pulling all of these rocks towards the centralized point of the Earth, increasing the pressure. The insides of the Earth are hot because of radioactive decay. At the beginning of the course, we talked about how radioactive decay is a method that we can use to help us to understand the age of rocks. Everything that we've learned about the age of the solar system and how the solar system formed and how the moon formed is largely based upon our understanding of the ages of these rocks from radioactive decay. Now, radioactive decay, in addition to being very, very useful for helping us to understand age, is also important because it helps us to understand why there is heat inside the center of the Earth. As every little molecule of radioactive material decays in the insides of the Earth, you can multiply each of those molecules by trillions and trillions of atoms, and that's trillions and trillions of tiny little pockets of heat that, when you combine them together, makes a tremendous amount of heat. So the inner core is the hottest part at the center of the Earth, and that heat gets less and less and less the farther you get until you get to the crust, and we can obviously walk on the crust of the Earth. In most places, wherever liquid rocks from the interior of the Earth come out of the crust, that's called lava, and you don't want to touch that lava because that's thousands of degrees Celsius. That's sort of a reminder to us that the interior of the Earth can be very, very, very hot. And that lava is coming from places not too deep, actually, usually from the asthenospheres where most magma turns into lava on the surface. We can think of different types of liquid rock depending upon where they're located. Magma is the term that we use for liquid rock that is under the surface of the Earth. And in Austin Powers, that's where you hear Dr. Evil saying, "Liquid hot magma, Mr. Powers." He's actually incorrect in the movie. By the time that liquid rock gets to the surface, it is then lava, but liquid hot magma sounds funnier. Then once that rock gets onto the surface, we have a name for it. It's called lava in its liquid state. So the mantle is the next portion of the Earth underneath the crust. This is a good opportunity for us to talk about how this diagram is not to scale. Okay, scale means correctly comparing the size of different things. This diagram, the purpose of it is for me to help you to understand the different layers, but if we're talking about actual scale, this picture that we started the video with is much, much more to scale. Look at how thin the crust is compared to the rest of the Earth. The Earth is 6,000 miles in diameter, and remember what we said about the crust? The crust is at maximum only about 30 miles thick. So this crust layer is very, very thin compared to the rest of the interior of the Earth. And if we go to our diagram here, the mantle is thousands of miles in diameter. Okay, what about the outer core, the next layer? The outer core is liquid due to the combination of intense heat from the core and increasing pressure from gravity pulling the rocks of Earth inside towards a centralized location. The outer core is arguably the single most important part of the Earth's interior because the outer core produces the magnetic field. The magnetic field protects the Earth from solar wind in combination with the atmosphere. That's why we have aurora borealis and aurora australis. The magnetic field is funneling solar wind around the magnetic field to the poles, and that's why we see those beautiful shimmery colors that are at the northern and southern latitudes, depending upon how much solar wind is striking the Earth. So, why a magnetic field? Well, the outer core is mostly composed of magnetic rocks that are moving around in that liquid state, and it takes a really long time for them to move around, thousands of years. But as they move around, the motions of those magnetic minerals and metals are producing our magnetic field. Down beneath the outer core is the most central part of the Earth, the inner core. The inner core is solid, under intense pressure, made mostly of iron, and that radioactive decay in the inner core is the source of Earth's heat. And so all of these differences between the different layers of the Earth are dependent upon two factors. The pressure from gravity pulling all of these rocks in, depending upon where you are, and then finally the tremendous heat that is produced in the inner core due to radioactive decay that is gradually and gradually and gradually making its way to the outer parts of the Earth. By the time that it gets to the crust, we can walk on it. We're not feeling a lot of heat from the inside of the Earth unless we are in a particular part of the Earth that is connected to the mantle, the asthenosphere. And that would be things like fissures and volcanoes. Volcanoes are sort of windows into the inner layers of the Earth, where the tremendous heat that exists down there can escape out to the surface. So thanks for watching. The goal for this video was for you to know and understand the basic makeup of the inside of the Earth. This is an important foundation for you to understand how rock is actually moving around down there, and we'll hit that up in a later video. In order for you to show evidence of what you've learned, please write your answers to the questions for this section and show it to your teacher so that they can check your experience. Thanks for watching.